I'm Aina, and I will be explaining generally on the external force convection. As per we know, convective heat and mass transfer is the process of heat and mass transport through fluid flow. As to that, generally, in external force convection, the fluid has at least one side that is not bounded by a solid surface. Flow over flat plate is one of the examples of external flow. However, I will be explaining generally just on parallel flow over flat plates as well as cylinders and spheres. So firstly, in external force convection, we have drag and lift, in which drag is the force a flowing fluid exerts on a body in the flow direction. Meanwhile, lift is the component of the pressure and wall shear forces in the normal direction to flow tend to move the body in that direction. As you can see on the screen, the formula given are to calculate the Reynolds number for parallel flow over flat plates. The explanation also explains how the transition from laminar to turbulent begins at around 1 to the exponent of 5 but does not become fully turbulent before the Reynolds number reaches much higher value, typically around 3 to the exponent of 6. And now, you can see the formula to calculate friction coefficient for local laminar and local turbulent, as well as the friction coefficient to find average laminar and average turbulent. And here, the formula given are to find the heat transfer of parallel flow over flat plates for local laminar and local turbulent, as well as for average laminar and average turbulent. Getting into cylinders and spheres, the figures and graphs shown on the screen are the drag coefficients for cylinders and spheres. There are a total of 3 graphs or figures which related to drag coefficients of cylinders and spheres. And now you are seeing the formula and parameters on how to calculate and how to get the heat transfer for local and average cylinders and spheres.
Assalamualaikum, I'm Nur Hazira bin Rashid. We'll explain about the internal force convection. First of all, it consists of laminar and turbulent flow in tubes. This is the equation which is we need to calculate the Reynolds number. And then this is a classification of the flow regime, which is consists of general, practical and extended, which is consists of laminar and turbulent. This is the classification of Reynolds number. Then this is the hydraulic diameter DH, the equation. Then it is consists of circular tube, square duct, rectangular duct and channel. It is different formula. And then this is the entrance region for hydrodynamic. And then this is entrance region for the thermal. Then this is the entry length, which is for laminar and turbulent, the equation. And then it is the graph that explain about the both and u higher in the entrance region and both and u identical in the fully developed region. Flow fully developed for x more than 10 diameter. And then this is general thermal analysis Q, and then constant Qs also Q0. And then this is constant ES Q, PM, which is a mean fluid temperature. This is also the graph. And then this is laminar flow in tubes, which is about the pressure loss, a pressure drop due to viscous effects. And then this is about the pipe head loss, the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in the pipe. This is the end tube for entrance region, circular tube. This is the turbulent flow in tubes, and this is the end tube for friction factors, smooth tubes, which is consist in the equation. This is the fully developed turbulent flow with rough surfaces. Colbert equation, which can be easily accessed via Moody chart. This is flow through tube annulus, hydraulic diameter, DH, NU, correction factor, F, and this is the end. Thank you.